Morning, everyone. First of all, there is one new assignment posted, and it consists of two parts. One of them is online, so exactly like the skills module, but now it's all material that we cover in the class. So basically lines, equations of lines, circles, distances, functions. And the second part is offline, so there are 3 questions which are posted on our website, the website for section, and there we have to give full answer. So the problem will ask you something like find the two circles, and your answer should be just two equations. It should be let's denote by such and such vectors the following unknown quantities. In this case, the equations of the circle is such and such, because such and such form lies in such and such circle, the following equation holds, expanded, solve the following system, and your answers, and then answer in words, something like this. So full explanation, the full solution should be in one text, not just random bits and pieces. Full text should be self-explanatory. And also there is one new skills module posted. So the skills module is about high school material. It's not due next week, it's due in 2 weeks. And well, my suggestion for you would be kind of to split the work between this week and next week, because there will be a new assignment posted next Friday as well. So it's kind of a lot of work. So try to pace yourself, try to do a little bit of it. Start doing it tomorrow if you have time, do a little bit more on Sunday, and aim for more than half of it, or maybe half of it will be finished by the end of the weekend, and during the week, finish the rest of it. Yeah.
Assignment 1, is it labeled as like assignment 1.3?
Yes. So it's labeled as 1.3. First assignment.
No.
It's using third week classes. Other questions? Yeah. You should bring it in class, yes. Next Friday. By the way, I want to ask you, how many of you found the algebra skills module difficult? How many found it okay? And how many found it easy? Wow. Okay. Well, so if you found it difficult, it means, well, by doing it, you actually learned a lot. So it's kind of positive. Yes. Read homework also next Friday. So both the read part and the offline part will be next Friday. So offline part, there is assignment posted on our website, and you should actually write down full solutions and submit the hard copy. Okay, so back to our material. Last time we talked about functions, and we finished last class talking about the graph of functions. So if you recall what we did last time, graphs of functions. If you have a function f which takes an input x and outputs output f of x, then you can draw the set of the collection of all points of the form x, comma f of x. Or in other words, all points, i.e. points x, y, with y coordinate being f of x. So if you have x, you draw a point whose height is f of x. And we had an example of one simple graph. Example, if y was, sorry, if f of x was the function 2x plus 1, we figured out that the graph consists of points of graph consists of points with y equal to f of x, which is 2x plus 1. And we figured out that we actually know how the graph looks like. This equation is the equation of a line, and y-intercept 1 and slope 2. So it's such a line. And also we discussed that given a graphical function, you can know what the function is, well, not quite in terms of a formula, but rather what it does. So if you want to figure out what the value of this function is at the point, say, 3/2, you go to x, which is 3/2, you measure the height of graph over this point, and this thing should be f of x. In this case, I'm not sure. It's 1, 2, 3, or a little bit below. So my graph is not accurate enough, but if you draw it on actual graph paper, you should get better results. So let's remind what we did in the first class. Now let's have some more complicated graphs. So another example. Function which takes its argument and squares it. How does its graph look like? Well, unfortunately the graph, which is y equal to x squared, is not one of the equations that we discussed. It's not an equation of a circle. We don't have x squared plus y squared equals something, or x minus something squared plus y minus something squared is equal to something. It's not an equation of lines, so it's not a times x plus b times y is equal to c, or y is equal to b x plus mx plus b. We have this x squared, so we shouldn't discuss this graph. On the other hand, we can figure out how it looks like. And what we do is just, first of all, draw a couple of points on this graph, then try to argue about the rest of the points being somehow on this general shape, so we figure out the general shape, and then we'll draw the graph. So let's start with some points. Some points. We have x, and we'll have y, which is x squared. So we choose the values of x. First of all, we'll go with 0, 1, minus 1. So we'll cover these things near the origin. When x is 0, x squared is 0. When x is 1, 1 squared is 1. Minus 1 squared is also 1. Minus 1 is 1 is 1. So let's start with these 3 points. 1, 1, 0, 0, minus 1, 1. Next, maybe let's continue to 2 and minus 2. So both 2 and minus 2 will be able to produce the same output before. So let's stage these points. Go 3 steps up from here. So first we need to notice, as I go to the right, as x increases, the function also increases. So that's quite obvious. The larger x is, the larger x squares. Another thing to notice, which we already see the pattern here, it kind of increases faster and faster. So if you increase x, let's say, by 1, if you increase it from 0, y increases just by 1. If you increase it from 1 by 1, y increases by a bit more. If you increase it by 1 from here, so at point 3, y value will be 9. So it will be really large. So I would say that from here, it kind of increases and increases faster and faster. Also from here, as you go to the left, it's kind of symmetrical. So you see that it doesn't matter whether you put plus or minus sign in front of the input, the output is going to be the same. It's because minus x squared is the same as x squared. So we can draw a similar thing here. Near the point 0, we'll have to be a little bit careful. So there is something happening here, obviously. So the function used to be decreasing, then it looks like it will be increasing. Let's investigate it a little bit more. So let me add the points 1/2 and minus 1/2. The output is going to be 1/4. I go here, draw the point 1/2 minus 1/2, and the height here is actually quite low. It's only 1/4. And I see that this function decreases to 0 somewhat fast. So if I go to 1/3 here, the height will be 1/9, which is more than 2 times as low as this point. So 1/3, 1/9. So it decreases rather fast. And now I can reasonably connect it like this. Now, this shape is of course not 100% accurate. I did not plot the points 1.5, 1.7, 0.1. They're not accurate. Also, my sketch itself is not accurate. But the sketch reflects some things which were actually interesting about the function. Is it increasing or decreasing? Well, I look at the sketch, it looks like it decreases all the way to 0, then starts increasing. Does it increase faster and faster when it is increasing? Well, yes. So it increases and it increases faster and faster. Does it become really large when x is large? Yes, it does. So you can see all these features reflected in this graph. So this graph is useful. Even though it's kind of sketch, it's not 100% accurate, still it's useful. So questions about this graph? Let's try another function. Somewhat similar, but you see that the graph is actually quite different. So the function takes its argument and computes the third power. And let me do the same thing. I'll choose points x, compute f of x, x cubed. I'll start once again with 0, 1, minus 1, 2, minus 2. So 1 cube, 0 cube is 0, 1 cube is 1, minus 1 cube is minus 1, minus 1, minus 1, the product is minus 1. 2 cube is 8, minus 2 cubes is minus 8. So let's start sketching. I put the point 0, 0, 1, 1, minus 1, minus 1. So just these 3 points are really not enough. From these 3 points, I would guess that my graph is actually a line. It looks like these 3 points line a line, but we'll see in a second that it isn't. So you shouldn't stop when you have just a few points. You should have enough points to get a feeling for how the function behaves. So at the point 2, y is really large. It's 8. So it is somewhere here. Let me put the point as high as I can. At minus 2, it's minus 8. So let me put the point somewhere here. And once again, one of the features of this thing is as you increase x, x cubed increases first of all, and as you go to the right, it increases faster and faster. So 2 cubed is already 8, but 3 cubed is really large, it's 27. And 4 cubed is 64, so it increases and really, really fast. And also we'll have to be a little bit careful about this point 0. So how does the function behave near the point 0? It looks like, well, you see what kind of feature we have here. So we compute this 1/2 and negative 1/2 points. At 1/2, the output is 1/8, minus 1/2 is minus 1/8. So my function at point 1/2 is really, really small, 1/8. And minus 1/2, once again, is really, really small, negative, minus 1/8. And for points which are close to 0, my function is really, really close to 0. So if my point is 0.1, my function is 0.0001. So it's really, really approaches 0 really, really fast. So I'll probably connect these points by such a graph. Something which goes to 0 really fast, and then kind of symmetrical thing. Because now, if I add a minus sign to the input, the output also changes. So this graph is symmetrical. So this function is increasing all the time, but how fast it increases, well, here it increases fast, here it increases slower and slower, until here it barely changes, but then it starts increasing fast once again. So, one moment. I kind of already knew how the graph is going to look like because I tried to do it on my own a couple of times. On your first attempt, well, it might be not immediate that you should investigate the neighborhood of point 0 closer. It also might not be immediately obvious that once you computed f of 1/2, how to connect the dots. Is it really kind of like this, or is it more kind of touching the x-axis, or is it going through the x-axis like this? So it's not really that obvious. If you want to produce an accurate graph, but you did not produce enough points to do this, we'll produce a couple more. It's easiest done with a calculator. It's even easier with a computer, which can actually compute huge tables like this. But basically, the technique is the same. So take enough points on your graph, maybe reason a little bit about how the function behaves overall. Like here, if x is positive and I increase it, my function is going to increase, obviously. So we have the symmetry, so some features we argued about, but mostly we just relied on points. Okay, so questions about this graph? Okay. One last function which I want to discuss is this function, absolute value of x. So first of all, what is the function? Let me recall what absolute value of x is. It's the function which takes its input, a number, which can be positive or negative, and outputs basically the same number, but disregards the sign. It always outputs just the magnitude of this number, without the sign. So for instance, absolute value of 5 would be 5, and also absolute value of minus 5 is going to be 5. So absolute value takes an argument and disregards the sign. So absolute value of 5 is going to be 5, minus 5 is also going to be 5. If we want it's at 0, it's going to be 0, and more generally, if you apply absolute value, so if x is positive, this number x without the sign. So how this function looks like? Let me not write the whole table. It's a pretty simple function. F of 0, absolute value of 0 is 0. F of 1 is 1. F of 2 is 2. In general, for positive x, f of x is x. And we know that the graph of f of x is x is a line y equal to x. But this works only when x is positive. So I have such a line when x is positive. The slope 1 goes through the origin. This line is y equal to x. Let's see what happens when x is negative. X is negative 1. Absolute value of negative 1 is 1. Absolute value of negative 2 is 2. And absolute value of negative 3 is 3, and so on. So here we have a similar line, but the slope negative 1. So we draw a central line. And this is our first example of a graph which doesn't look kind of smooth. It looks somewhat broken. So it goes like this, and then it suddenly changes the way it goes. There is a breaking point, and then it goes in this direction. So unlike these graphs, which are smooth, so you go and you never have an abrupt change. Or this one, so you have a small change around 0, but it's not abrupt. Here we do have this abrupt change. So like this, then suddenly you turn and continue this way. Questions about this function? Let's look at this graph and forget that it came from the function absolute value of x and think how we will describe it just based on seeing this graph. Function now I want to say something like this. This function f of x is x when x is positive and minus x when x is negative. That's what it is. So this is the graph of y equal to minus x, and this is the graph of y equal to x. This is a line which has slope minus 1. This is a line which has slope 1. And so in symbols, we usually write it like this. The function is defined by kind of cases. It's x when x is positive, and it's minus x when x is negative. So this notation, it might be new notation, is a function which is defined by different formulas in different ways based on different conditions on the input. So if the input is positive, the function is x. If the input is negative, the output is minus x. Let's see that this function is actually the absolute value. When x is positive, think something like 5. The function produces just x, which is 5. If x is negative, think minus 5. So the function produces minus x, which is minus 5, which is exactly 5. So this function is in fact absolute value of x.
So the last part, right?
So if the input is negative, think about something like -5. What's going to be the output? Well, according to this rule, we go according to the second definition. The input is negative, we go along the second definition, and the output is going to be minus the input. The input was -5. What is minus -5? Well, this 5. So even though this function, well, looks a little bit more bizarre than this one, it's defined in different ways for positive numbers, for negative numbers. It adds kind of negative sign to already negative number. It is actually doing exactly the same thing. It gets rid of the signs. And more generally, okay, so first of all, questions about this remark. Yeah?
X is less than 0, then how is, like in the example of the -5, how is the answer positive?
Okay, so let's think about x being -5. According to the definition, when x is negative, the output is going to be minus the input, minus x. So here we're doing exactly this. The output is minus x. X is -5. So this is x. What is minus x? What is minus -5? Negative of negative is positive. So this is 5. Other questions? So in general, sometimes you just have to define a function using cases. Some natural functions are defined in different ways depending on different values of the parameter. Examples would be, maybe you're heating ice, at some point it becomes water, all the physical characteristics of water are different from those of ice, and then the temperature, the graph of temperature will not be given by the same thing, it will be something like this. The ice gets heated in one fashion, then there is a transition around 0 degrees, where the overall temperature is not changing, then it all becomes water, and the heat increases, but maybe at a different rate. The temperature increases, but at a different rate. So there are some quite natural equations where the output kind of depends on what kind of input we give to the function. So maybe let me give an example which is with more applicability to everyday life. So another example, function defined by different cases. So let's talk about the income tax system again. So income tax as a function of taxable income is more or less the following function. First of all, it is 0 if your income is below 10,000. I'm not taking the exact numbers for Canada, they change from year to year, but approximately that's correct. Then, then the income is taxed, so the income over 10,000 is being taxed at a rate of 15%. So if X is larger than 10,000, then you pay 15% of X minus 10,000. But this rule also doesn't apply to any X, which is larger than 10,000. Actually, you stop when X is 40,000. And then you pay even more tax. So if X is larger than 40,000, you pay 22% of your income over 40,000 plus, well, whatever you pay for 40,000, which turns out to be 45,000. And finally, oh yes, so this rule also stops at some point, 80,000. Yes, tax system is complicated. Then you pay about 26% of the income over 80,000 plus whatever income, whatever tax you already paid in the previous case, and this rule works whenever the income is above 80,000. So now we covered all the cases. Whatever the input is, whatever the income is, you know that you will be covered by one of these four lines. If X is smaller than 10,000, between 10,000 and 40,000, 40,000 and 80,000, or greater than 80,000, you will find what to do. Actually, in real life, there is one more tax bracket, which is around 130,000, and it starts at 29%, but well, it doesn't matter. It's example. And of course, you can ask what the graph of this function looks like. It looks like, well, first of all, f of x is 0, has a really simple graph. X, y. So I won't draw the graph to scale, but just to give a feeling for how it looks like. F of x is 0 has such a graph. For every x, the output is 0. Then at 10,000, suddenly you start paying tax. And what kind of function is it? It's y equal to 0.15 times x minus something. So it is a linear function. The slope 0.15. So there is some slope, 0.15. And here the function should match this one. So when x is exactly 10,000, you still pay 0. Then you get to the next bracket, which is 40,000. The next function is still linear. Y is equal to 0.22x plus some number, or minus some number. Well, it's a linear function, and once again, the tax system is constructed in such a way that there is no sudden jumps. So if you earn $39,999, if you increase your income by $1, your tax is not going to jump by thousands. So it's a line which still passes through this point, but the slope is a little bit higher. So the slope is the percentage of tax being paid in this case. So we draw a line with slightly higher slope. We continue until 80,000. And here we have one more line whose slope is even larger, but just a little. So here's the graph which explains how the tax system works. You are not taxed all the way until 10,000, taxed a little bit until 40,000, taxed more until 80,000, and even more after that. So let's talk about transformations of graphs. Let's imagine that I give you a function and I give you the function as a graph of this function. So let's say it passes to the point 0, 0, 0, then it goes to the point 1, then it comes back to 0, 1, then increases. So something like this. One, two, three, 0, this is 1. So some function of this shape. I don't tell you what the function is. I don't give you the formula for this function. I don't tell you how to compute it for any input. But you see its general behavior. So this is the graph function, graph of elements. My question is, what if I produce a new function? Let's say the same function but multiplied by a factor of 2. So how would the new graph of 2 times f of x, how will this look like? Yeah, let's think about it. So the new function is the old function multiplied by 2. First of all, try a couple of points. If I plug in 0, well, my old function gave me 0 as an answer. My new function is going to give 2 times 0, which is still 0. If my input was 1, my old function gave me an answer of 1. The new function is going to give me an answer of 2. Well, if my input is 2, output was 0. Here, it's still 0. Then, for 3, the output used to be 1, now it's going to be 2. For 4, well, it used to be something like 4, now it's going to be 8, somewhere over there. For minus 1, the output was minus 4, now it's going to be minus 8. So what happened to the overall shape? For every height, whatever it used to be, now I should draw twice the height. So what I did, I just stretched the graph by a factor of 2, but only in vertical direction. So if you imagine that it was kind of drawn in some kind of rubber, you pull it twice as much, and now you produce a graph which is so instead of this small mountain being of height 1, now it is of height 2. So it's much sharper. So this shape is just the whole graph, straight by factor of 2 in vertical direction. First observation, if you draw the graph of some number times the function, what happens to the graph? It just gets stretched by this number. Actually, it only works for positive numbers. Let's see what happens for negative numbers. Graph of negative numbers. Well, once again, let's start with a couple of points, and then we'll figure out the pattern. So the new function is point 0. Here it was 0, here it's minus 0, so still 0. At point 1, f of x is 1, minus f of x is minus 1. At point 2, f is 0, minus f is 0. At 3, f is 4, new function minus f is negative. At negative 1, old function is negative 4, new function, which is minus f, it's minus 4, which is 4. So here, 4. So how is this new graph related to the previous one? Inverse, yes. So it's basically a reflection of the old one. I take the old one and invert it around the x-axis. So how does it look like? Somewhat like this. So think about this thing and flip it around the x-axis. So when you multiply the function by minus 1, you get a minus sign, the effect on the graph is flip around the x-axis. Okay, let's try a couple more. Graph of f of x minus 1. What's going to happen here? Well, this is maybe even easier. So let's do it like they always do. At 0, f is 0, f of x minus 1 is going to be minus 1. At 1, my function was 1, so the function minus 1 is going to be 0. At 2, it's going to be minus 1. At 3, it's going to be 3. At minus 1, it's going to be negative 5. So what happened to the graph? Shift down, yes. So whenever I have a height, some height here, y, the new height is going to be y minus 1, one smaller. So the overall shape just shifts down by 1 unit. Connect these dots. Something like this. Oh wait, at 3 it used to be 1, so this 3 is 4. So it goes to 3, 0, and then goes to 3, and x is 4. So such a shape. So if you add a number to the function, what happens to the graph? It just shifts. If you add a positive number, it will shift up. Negative number, like here, shifts down. Let's have one last one. But actually, one more complicated. So, graph of f of x plus 1. So, this function. First of all, what does it mean? It's a new function, and then given a name, g of x, which behaves in the following way. You give it an input x, and the output is the value of the function f, but not at the point x, at the point x plus 1. So let's try. When I take the input of 0 to this function, the output is going to be the value of f, but at the point 0 plus 1. So f of 1. I go to here, f of 1 is 1. So at 0, the value of my function is the value of that function at point 1, which is 1. So here's my first point, 0, 1. Right, somewhere explicitly what I did. My new function at the point 0 is the value of old function at the point 0 plus 1, which means f of 1, and in this particular case, it happens to be 1. Okay, at point 1, the value of my function at the point 1 is the value of f at the point 2, which happens to be 1. So here's the point. Next, at point 2, the value of g is the value of f at the point 3, which is 1. At 3, the value of new function is the value of f at the point 4, which is 4. Let's go to minus 1 and minus 2. So g of minus 1 is the same as f of minus 1 plus 1, which is 0. Which is 0. And finally, at negative 2, the value of my function is the value of f at the point minus 1, which is minus 4. Okay, so tell me what happened to the graph. It shifted to the left, exactly. So this one is probably the most confusing. You are drawing the graph of f of x plus 1, but the effect is shifting the graph not to the right, but rather to the left. And you see it in this example. And vice versa. If you wanted to draw a graph of f of x minus 1, the graph is shifted to the right.